purpose of our training for you experienced inspectors. We want to revisit previous training topics in areas that continue to be problematic, reinforce proper procedures. For you new or less experienced inspectors, we want to provide you with information that will put you on the right track to being successful. So help us out here, just for those of us who are doing the training. How many of you with 10 plus years of experience, structure inspector? Okay. How about 5 to 10? Okay. 3 to 5? All right. And how about no experience? Anybody with no experience? Good. Appreciate you raising your hand. That's good. Well, it's good to have all of you. I think it'll be a wide, I think you'll see some topics here. Hopefully it won't be over your head for those of you who are new to it. But certainly I think we'll revisit some topics for those of you obviously been around for a while. And also for our benefit, what divisions? We've got the 7, 8, 9, and 10. Any others? Okay. Very good. Obviously, you guys know where you are, Randolph County. We do have one more week's training 2 weeks from now in Marion. The format, it is a 2-day class. We will be going, you guys are the class 2 there, and we will be going 9 to 4 both days, today and tomorrow. Hopefully tomorrow you'll get out a little early. And odds are today, though, it'll probably go till 4 o'clock. That's just kind of the way things have been going. So, what are we going to talk about? We've got Dean Hardister, and Chris actually is not here, right? So Dean's going to cover geotechnical today. Lee will be talking about structure layout. Eddie and I will talk about elastomeric concrete and foam joint seals. We'll go to lunch. Come back and Lee will discuss drilled piers. We'll talk about cylinders and testing with Darren. Is Walton coming today? Do you know? No, Walton's not going to be here. And then Randy Dempsey from M&T will talk with us about welding and steel. Tomorrow, Aaron Earwood will discuss safety. Cameron Cochran will touch on decks and setup issues, and Larry Carpenter, concrete finishing, and Aaron will wrap it up with girder erection. There may be some swapping around of the agenda. You guys have an agenda in your booklet. I'll touch on the booklets now. I just thought about that. The agenda in your booklet probably doesn't quite match this, so don't get too bogged down with the times and everything that's arranged in there. We may switch some things around if we see fit, but we will be discussing all these topics. And just to orient you with your booklet, on the left-hand side, we've got, again, the agenda. We've also got a set of checklists for you that we've developed, some of which you've probably seen before. Some of them we have developed just for this training. So we hope that they'll help you in the field. We've got some for drilling, for deck pours, for construction stakeout, all the various topics that we'll be touching on here. There's also some information from Polyset, which is one of the products that we're going to use in the hands-on demonstration for the elastomeric concrete and the foam joint seals. And we have their manufacturer's instructions in there. And I'm seeing some Bidwell info in there as well. So on the right-hand side in your booklet, you've got the slides from the presentation. Now, I want to point out to you, every slide you're going to see up here is not going to be in your booklet. Okay, it would have been a super thick booklet, so we tried to trim down and actually put the slides we thought were important, so don't get hung up on the fact that, hey, I'm missing this one, it's not here. Just keep following along and you'll pick back up with where we are. So, anything else? No, I'm missing. Forget. Any questions getting started? All right, we'll turn it over to Dean. And I always mention the Sasquatch pictures I can't really explain unless you are familiar with Nobby. I don't know if you guys are in this part of the state, but be sure to ask Larry Carpenter tomorrow. Larry being here tomorrow, he can explain that a little bit.
Good morning, everybody. I'm Dean Hardister. I'm the Western Region Operations Engineer for Geotech Engineering Unit. I cover divisions 8 through 14 for foundation issues, soil, rock, groundwater problems, anything related to geotech. Chris Kreider had another meeting to go to today. He's the Eastern Region Operations Engineer. And I'll try to cover all the geotech issues with regard to pile driving today. Since October, any project that was going to be let from October 2010 till the future is governed by a design process called LRFD. It stands for Load Resistance Factor Design. It's different for those of you that have seen recent projects being let. You probably notice notes, structural notes change in the plans. If you remember the old way of doing things, we would, structure design also, but geotech mainly, we would design a foundation and apply a factor of safety to it at the end of that design. For piles, if you remember, we used to have, 10 or 15 years ago, we had 45-ton piles, and you may grab a bridge maintenance job that's being let, and you may still see 45-ton piles, but we would have 12 by 53s, 45 tons or 50 tons. We slowly crept up until we had 60-ton piles, and you would notice the note on the plan would say, the piles are designed for an allowable bearing of 60 tons. And it would say, drive the piles to a required bearing capacity of 120 tons. So there's that factor of safety of 2. Well, the design process isn't the same anymore, both for structures and for geotech. And the way the design process works now is, as we're designing that foundation, different resistance factors are applied. And when we don't have great confidence in something, that gets a smaller resistance factor, thereby reducing the load that we put on the foundation. But in areas where we've got good confidence in what we're looking at, then that resistance factor is bigger, meaning we can put more load on it. So similar process, but it's just at a different part of the design stage. How does this affect you guys? Well, as I've said, if you've looked at a recent letting, plans from a recent letting, what you're going to notice is we don't have 60-ton piles anymore. It'd be a rare situation unless you get a bridge maintenance job or a job that sat on the shelf for a few years. What you're going to see is the notes on plans would say, piles are designed for a factor of resistance of whatever, and it might be 120 tons on that pile. The following note would then say, we're going to drive that pile to a driving resistance of whatever, 180 tons or 200 tons. So we're driving these piles a whole lot harder than we ever used to. When you drive a pile to 200 tons, it takes a big hammer to drive that pile. No longer, when I first started 6 years ago with the state, it wouldn't be uncommon for a contractor to submit a Delmag D12, which is a 2.5 kip ram, and a Delmag D19. Well, as the LRFD has come out, the D12 goes away because a 2.5 kip ram and a hammer is not enough to get anywhere close to 150 tons on the pile. So with higher pile loads, you see bigger hammers, and with bigger hammers, you see bigger cranes. Takes a lot more stroke, even if you've got a Delmag D1942 4-kip ram. It takes, 7 or 8 foot stroke to proof out that pile to 200 tons, if that's what we're looking for. Okay? So your job is going to change if it hasn't already. Those are the new notes that we use, as I stated before. We talk about nothing is bearing anymore, it's all resistance. Same meaning, different words. If you, the skinny on all of this is, if you look at that first note that says the foundation's designed for a factor of resistance for piles, if you take that factor of resistance and you divide by 0.6, you get the driving resistance. Okay, so that's the skinny on the resistance factor. And you might say to yourself, well, piles used to be designed for a factor of safety of 2, so shouldn't that resistance factor be 0.5 instead of 0.6? Well, a lot of research and everything went into that, and AASHTO set that resistance factor. Now, we varied away from AASHTO a little bit and are using that 0.6 factor. And just so you know, a lot of probability and statistical analysis and everything was done to come up with that 0.6. Ultimately, it's the same as we've always done it, but it just looks a little different. If we run PDAs, AASHTO now prescribes, the current 5th edition of AASHTO prescribes at least two PDAs, or 2% of the piles, and we have very few projects that 2% will be more than 2. So if we run 2 PDAs, again, it comes down to a confidence level with those resistance factors. So if we've got, say, 12 in-bent piles for a job, if we drive 2 of those, we've got a pretty good confidence on the remaining 10 that we do, that if we use the data from those PDAs, we're going to have confidence that the other 10 are just like what we did with the PDA. So our confidence level goes up, and our resistance factor then goes up as well, or our factor of safety can be reduced, and so we use a resistance factor of 0.75, which means we run 2 PDAs. If we incur the cost, roughly around $3,000 for a PDA, if we incur that cost, what that buys us is a little more capacity, or the same capacity with less risk of damaging that pipe. Okay. In North Carolina, when you're driving piles, there are typically 2 conditions. You've got high tip resistance conditions, which is really my part of the state, western part of the state. Most of Division 8 and everything west, 7, same way. Anywhere that you don't have coastal plain, they tend to be tip resistant piles. From 8 and east, all the coastal plain divisions, they tend to be skin friction piles. Big sections, pipes, square concrete piles, something that they're called displacement piles. As you drive them in the ground, they're displacing material. So you develop a lot of skin friction by doing that. Tip resistance piles tend to be driven to something hard, weathered rock, really hard clay, dense sands. They tend to be relatively short piles. My part of the state, piles will tend to be from 10 feet to 30 feet. When you get longer than that, it's a rare condition. The eastern part of the state, coastal plain sections, they tend to be skin friction piles, really long, 70, 80, 90 feet long. It takes that much pile to start displacing, the material to develop all that skin friction, plus the stiffness of the soils in the coastal plain tends not to be as high, so it takes a really long pile to get the tonnage that we're looking for. Thing to keep in mind, west and east in this state is fairly distinct, but there are places, I've seen Stokes County where we had 80-foot long piles, nothing to tip those in. Hendersonville, over in 13, same situation. So just because you're in the western part of the state or in Piedmont ground doesn't mean that you're not going to end up with skin friction piles. Pile driving is broken into the analysis side, the design phase, where you guys really never see the work going on. You got construction submittals, the hammer pile driving system that the contractor submits, and then the construction side, which you guys are always involved. Once the contractor wins a contract, typically one of the first submittals they make to to us is the hammer submittal. And that hammer submittal will list at least one hammer, typically two. And it's everything about the hammer pile driving system. It would include the helmet weight for the hammer, hammer cushions, and if you're driving concrete piles, it may have a pile cushion, a plywood cushion for driving concrete. We use a software called WEEP to look at that pile driving system. And it's not only the hammer, but it's also the weight of the pile figures into all this pile driving. If you can imagine, if you've ever been on a project that you had 20-foot piles that indent one and 80-foot piles that indent two, and you look at those two driving tables are totally different. Well, an 80-foot long 12 by 53 is tremendously more heavy than that 20-foot long 12 by 53. So if you imagine running into something that weighs, 4 times as much, it takes a whole lot more energy to move that. And that's why those two driving tables are so much different. That hammer has to work a whole lot harder to shove that 80-foot long pile into the ground. What WEEP does for us is, and WEEP is made by a company called GRL, who developed research for the last 40 or 50 years pile driving. And using a database full of hammers and their typical operations and everything else. When a contractor submits, say, an ICE I-19 hammer to us, we go in that database and throw it into the software. That software will analyze that hammer operation and provide us the driving table that we give to you guys. Just so you understand, WEEP tends to overestimate the blow counts that it takes to get the tonnage that we're looking for, and it also overestimates the stress. That's important to understand because if we tell you to cap out the stroke at, say, 9 feet for a given hammer, that's probably a conservative estimate. We can probably go to 9.5 or 10 feet and still be okay. But as rightly it should be, the software tends to be a little bit conservative. Okay? We want to make sure that if we tell you 48 blows a foot gets us 200 tons, we want to make sure that truly 48 blows does what it says, if not more. There are two conditions in pile driving. First condition is a condition you guys probably are dealing with 95% of the time. And that's called the end of initial drive. That's the first try at driving that pile to bearing. What the spec book says is we're going to drive that pile continuously until we get, now it says resistance. The old way is bearing, until bearing is achieved. We get refusal blow counts, or the other condition is you've at least penetrated to the minimum tip elevation, if that by chance is on the plans. Okay? There are times that a contractor, let's say we had a contract that the average pile length is 40 feet. There may be times that a contractor, when he gets to 40 feet, he may choose to stop. Let's say we don't have bearing. Contractor chooses to stop and come back the next day and try to achieve bearing, letting that soil set up, trying to freeze that pile. If the contractor chooses to do that, then we don't pay the contractor to come back the next day and redrive that pile. That does not constitute a pile redrive, correct? Everybody agree with that? Contractor can choose to stop. If he chooses to stop, that's his choice, and we don't pay for the pile redrive. On the other hand, again, same contract, 40-foot long piles. If we get to 40 feet, we're not sure, we're getting nowhere close to the sets for 10 blows that we're looking for. We can step in and ask the contractor to stop driving. Okay, we're trying to save money. We're trying to hit the contract length. We don't want the residents to suffer project overruns and all of that. If we step in and ask the contractor to stop, then we're going to come back to him and say, we're going to wait 24 hours and we're going to come back and redrive this pile. If we do that, then when we go back and try to drive that pile, we will pay him for a pile redrive. Okay?
Are you seeing more redrives up here in this part of the area, Dean, because of the bigger hammer?
No.
No.
No, I mean, I would venture to guess that at least 90% of the projects in all the divisions represented here, till you get in part of Division 8, where you're into the coastal region, most of the time we're driving the weathered rock or something. But, you had the job up in Stokes that, 70-foot long, 80-foot long piles.
Are you seeing damaged piles from the bigger hammers once you get rock?
No, it's understand too that when we look at a hammer submittal, let's say we've got 10-foot long piles driven to hard rock. My philosophy is I would prefer a contractor at that point to submit a D12, okay, not a D 1942, because our philosophy is if you can get a pile of rock, we don't care really what the blow count is at that point. We're calling it good. We're calling it able to get any kind of capacity that we're looking for. So we would rather have a smaller hammer with less potential to damage that pile. So a really small hammer at that point is a good idea. So we look at things like that to make sure that we're smart in driving the pile.
So when we submit our pile hammer submittal, let's say for some amount, we're looking for the size hammer that they're submitting to make sure we're not doing the D19.
Yeah.
So much on the pile.
Yeah, a lot of times what contractors are having trouble with a lot of times is trying to get a hammer that is too big.
Right.
Rating a hammer based on the tonnage and not really looking at the entire system. And we reject a whole lot more hammers now for being too big than we used to.
So if these guys get a D19 and they got a high rock line, they need to.
Well, yeah, we'll handle that in the,
Just in case y'all.
yeah, yeah. And we'll, the memo that comes back to the resident and eventually filters out to the inspectors in the field, we'll provide guidelines in that memo that says, hey, we're driving it to rock. If you hit rock and you don't see any penetration, stop the driving. Okay, so it's important to look at the borings, know what we're driving to. If we've got weathered rock, it's okay. That pile will cut a little ways and then it'll stop. But if it's hard rock, ringing hard rock, and it shows on those boring logs, just understand that when that pile reaches that point, it's going to stop, and we need to get off that pile as quick as possible. The biggest risk for you guys, and you can't let the contractor get impatient. And a lot of times when we've got ringing hard rock really close to the surface, that means we've got a bunch of crap up above it. And it's, they stand the pile up in the template, they get the hammer sitting on top of it, and it sinks down 3 or 4 feet, and they try to fire that hammer up. It never fires because it doesn't have any resistance. It can't throw that ram when it hits that pile. It can't throw that ram back up in the air where it needs to go, and you never see it coming out of the hammer. So they get impatient. They sit there and start jacking the fuel up, and all of a sudden it starts firing. It hits that rock, and it almost comes out the top of the hammer. That's the last thing we want to have happen. We'd rather, if we know we're going to get to something hard, just tell them to be patient. Get it down there. That way we make sure that we don't get a 10-foot stroke when we're sitting down on rock, because you will damage that pile at that point. Does that make sense?
In a design build scenario, is anything really changed much from looking at it and all that?
Anything different on design build, Jeff?
Yeah.
A whole lot more tonnage on those piles, isn't it? Yeah, design build will, for those of you that have never been involved in design build, it is night and day from in-house projects to design build. You might be on an in-house project and you might see 180 tons on the 12 by 53 now driving resistance of 180 tons. Jeff's got the design build going on just right down the road, and they had 12 by 53s with 225, 230 tons on them. And you can get there, and we make them PDA to make sure that everything's okay. But you'll never see stuff like that on in in-house. Not now. It may take us 5 years to get there. But we're a whole lot more conservative in-house than design build is. So it is a lot different. Design build's a lot different. It always has been. Even before we switched, they had always put 200 tons on a 12 by 53, and we were never anywhere close. What LRFD has provided us in-house is to leave behind the old 60-ton piles, which meant we had to put a whole lot more piles under a vent to support it, and now that's given us the opportunity to switch and start going really where we should have gone many years ago. But there's always just been conservative thinking within the department. LRFD's provided us an opportunity to change that. So, but we're still conservative relative to what the construction industry can do. So. We'll talk about pile redrives. The most important, and this is typically for H piles that are driven and have nothing to stop that tip. A lot of times you'll be in a pile redrive situation. Okay, and the thing to keep in mind when you're trying to redrive an H section is if you hit that pile more than 3 or 4 times with strokes that aren't anywhere close to what you're wanting to see, you've wasted that opportunity and you're going to have to come back the next day. Okay? And do it all over again. Try to get it right the second time. So the most important aspect of a pile redrive is making sure that that hammer is smoking hot, ready to go when we try to hit that pile for the pile redrive. The best way to do that is if you finish the previous day's operations. We're sitting on an end vent, got 6 piles. We've driven all 6 of them, 3 of them got bearing, 3 of them didn't. The best way to warm up that hammer is to go to those piles that we accepted the day before and set that hammer on top. Now, your job as the inspector is to kind of know at the end of the previous day what our fuel pressure was for that hammer. And when I talk about fuel pressure, do y'all all know the little jack that sits out there and he pumps that thing up and it's got the dial gauge on it? Okay. The higher that pressure is, the finer the fuel into the chamber, the explosion chamber for the hammer. The finer the fuel, the bigger the explosion. That's why the higher you pump it, the higher that ramp is. So when we finish the day before and we know that we've got 3 that we're going to revisit, we need to know what that fuel pressure was from the day before, because that's the fuel pressure we're going to start at the next day when we do a pile redrive. So when we first come out there in that morning, the hammer's cold, it never wants to fire the first time you pump it up, it never wants to fire. We want to set up on a previously accepted pile, not one that we're trying to redrive, one that we've already got in the ground, we've called it good. Get it up to that fuel pressure, and we won't fire that hammer off until it's operating like it was the day before. That might take 10 blows on an accepted pile, it might take 20 blows. But we want it getting that consistent stroke that we were seeing the day before. Once we've got that, then we'll jump over to the piles that we need to redrive, because we want that first lick on that pile that we're trying to redrive to be just like the last lick was the day before. Okay? If we don't have a pile that's been accepted, we've driven 6 piles and none of them got bearing, then we need to get some crane mats out there to do the same thing. Same fuel pressure. You may not be able to get the same stroke as the day before, because the bounce off of a crane mat's not going to be the same as the bounce off of a 12 by 53 pile. Okay? But same fuel pressure, getting a good consistent stroke that hopefully we won't ruin that pile redrive. Okay? When we're doing a pile redrive, we need 2 people. And you might say, well, I don't have help out in the field, I'm by myself. That's okay. The part that I want the inspectors to do is to spot the stroke. Because in my opinion, if something's going to get screwed up, it's going to be the stroke, not the marking. Okay? So we'll put the contractor's laborers marking that pile. Okay? But I want you standing far enough back, if you've ever noticed, if you stand immediately under that under that hammer as they're driving, you look up, you're trying to gauge that stroke, you're always gauging high. Because your perspective's not the same when you're looking at that jump stick, that ram coming out. You're trying to get the marks on that jump stick. So you need to be far enough away that you can see that ram at the jump stick marks. Okay. Other thing is, hopefully before pile driving ever starts, you've got that ram. You make sure that that contractor has marked his jump stick right. Make him lean that hammer up. Make sure the ram slides all the way in. You pull the tape and make sure the jump stick's right. Okay? Okay? So during this redrive, we're going to tell the contractor this is 12 by 53, 14 by 73 H piles. Okay? Concrete pipes, different. They won't take off like an H pile will. But we're going to tell the contractor that we want to mark that pile every 2 blows. Okay? We're still going to drive it the 10 blows that we normally would, but we want to mark it every 2 blows. Your job as the stroke spotter, if you take my advice and you're spotting the stroke, is every 2 blows that you see, you're averaging those strokes and you're writing them in your diary. Okay? So when that 10 blows set is done, you can walk back over there and measure and write the 2 blow sets out beside those strokes. Okay? If by chance, and this would be a rare condition, consider yourself lucky at this point. If you get to the end of the 10 blows and you look at your driving tables for that given stroke, and you find out that the set for 10 blows that you just got on the redrive is less than what's in that table, great, we got married. Okay? Just like any other drive. I'd venture to guess that 95% of the time that isn't going to happen. Typically, we're not that lucky. If we're in a redrive condition, there's typically nothing anywhere close to the toe that's going to stop that pile. So what we're going to do then is we're going to look at stroke and what our penetration or set is for each of those 2 blows. And the way you figure out what a 2 blow set is, you've got a 10 blow set, and let's say you look at the table and it's 1 7/8 inches. If you take a 10 blow set and you're trying to convert that into a 2 blow set, you divide 10 by 5, and you get a 3/8 inch set for every 2 blows. All we did was broke that 1 7/8 inches into 5 seconds. Okay. What you're going to find out is if you're looking for a 3/8 inch set for 2 blows, what you're going to find out is in the first 2 blows, in a given stroke, you're going to see maybe a 1/4 inch penetration. Okay, so that's less than 3/8. The next 2 blows, blows 3 and 4 in that 10 blow set, it's probably going to be 3/8. But after you hit that 3/8, it ain't going to be 3/8 again. It's going to be half, 5/8, 5/8, 5/8. So if you averaged all those numbers, we wouldn't get to 1 7/8, or you added all those numbers together, we wouldn't get to the 1 7/8. It would not look like a passing check, bearing check. But what you need to do at that point is call the bridge construction engineer, call me or Chris, whoever you're supposed to contact. Have that data ready. What your stroke was in the first 2 blows, what that penetration was in the first 2 blows, so on and so forth. We'll make that decision. I won't straddle you with that requirement. We'll make that decision. You might say, well, that's a little bit hokey. That's like some black magic you guys are pulling out. Well, what you got to understand is when a PDA is performed, that's exactly what is done. You might, if you've ever been part of a PDA, you might do 2 or 3 10-blow set checks. When that data comes back, they're not looking at all 10 blows. They're grabbing one blow count out of that set check and saying, this is our representative capacity. Okay? That's exactly what we're doing. What happens with an H pile is, as soon as you hit that pile, you're losing friction in that pile. It's that vibration, that wave that goes down that pile, all the water that's in the ground excites all that soil, and it starts loosening up. Okay, that's partly what setup does for you. The day before, when you couldn't get bearing, all that soil was so excited it couldn't squeeze the pile. We wait 24 hours, all that excitation, all that excitement in the soil is gone away. That's freezing the pile. Okay, that's what's going on in reality. Well, that's why I said previously, it's so important to get that hammer hot and get that stroke where you wanted it to be, because the soil doesn't care whether you hit it with a 5-foot stroke or a 7-foot stroke. It's going to get excited. Okay? So if you hit it, if you're looking for a 7-foot stroke and you hit it with a 5, if you hit it 4 times with a 5-foot stroke, it's gone. It's done. We're back here the next day trying it again. Okay? Hey, yes.
So for all of us older people that remember that, we want to get on the pile and break it loose before we started counting, we don't do that anymore. We don't do that anymore. We want the 10 blows and stop.
Okay. How many folks have ever been part of a PDA test, have a PDA on their project? The way a PDA works is you mount gauges on the pile. Those gauges are accelerometers. They tell the computer how fast, when that ram hits that pile, how fast, how quickly it's moving into the ground. And again, the PDA was developed by the company called GRL. They researched it, did all the hard work. The reason we can drive piles a whole lot better today than we could 40 years ago. But what a PDA helps us with as engineers is it can measure the efficiency of that hammer system. It also can measure stresses in the pile, and it provides a good estimate of what the soil looks like in the ground. When we go into wheat in a pre-driving analysis of the hammer system, again, like I said, we've got a database of hammers. We choose that hammer, and that database is the collection for any given hammer, what GRL has seen that hammer do over the years. Okay. We also estimate soil parameters in that analysis because the dirt matters. What we're driving it through matters. What a PDA helps us do is refine, make those soil parameters better. Okay. When we get better parameters, we get better driving tables. And if you can imagine, as I told the group yesterday, not every Delmag D1942 operates like the next one. Just like you and your buddy might have the same vehicle and they don't operate the same. Well, that's all a hammer is a combustion chamber. So what the PDA helps us see is if I take a 4-kip ram out of a D19 and I raise it 8 feet, 8 times 4, 32, that's supposed to be 32 foot kips of energy, and that hits that pile. But what that PDA tells us is exactly what that energy was, and it's not going to be anywhere close to 32. So I've been involved in projects before, PDAs. Contractor rents a hammer, we go to drive the pile. We're not getting the bearing that we're looking for. Contractor calls the rental company and they say, oh yeah, that hammer's going to get the capacity. Well, the problem is that hammer wasn't operating at the efficiency that they expected it to. So we're not putting the energy into the pile. We can't, if you're trying to drive a pile to 200 tons, if you don't put 200 tons of energy into that pile, you're not going to be able to proof that pile. If that hammer can only put 180 tons, that PDA is only going to be able to tell you 180 tons of capacity. Period. Plain and simple. You might have 300 tons of capacity, but the hammer's got to be able to push it to 300 tons before you'd ever know it. Okay? We rarely run PDAs on H piles. Reason being is in-house we tend not to push the capacities. On design build you always have to run PDAs. Pile, at least one PDA for any driven pile for a given structure. For pipe piles, we tend to run PDAs for pipes because we tend to put a whole lot of load on pipe piles. And so we're confirming, one, that we're getting the capacity that we're looking for, and also making sure we're not damaging that pile as we're driving it. For concrete piles, how many folks have ever driven a concrete pile? They're aggravating. Hate concrete piles. They're not fun. We always run PDAs for concrete piles. The reason concrete piles are so aggravating is you tend to damage concrete piles. It's hard to drive a concrete pile, at least the way we set it up, in our standard concrete pile detail. When you're driving a concrete pile and you've got soft ground up above some layer that you're trying to get to or drive through, it's important to ease back on that hammer. And what the PDA helps you do is to monitor the stress. And with steel piles, we tend to be concerned with compressive stress. Concrete piles is totally different. We're worried about the tension stress because concrete's weak in tension. What happens in really soft ground, if you get too aggressive with the hammer, is as that wave travels down that pile, and it gets to the tip, that wave travels back up as well. Well, that wave is trying to stretch that concrete pile in this direction, which is bad. That's why cracks start to form in concrete piles if you get a little too aggressive. So that's why we always run a PDA, at least on the first concrete pile. We may do it on a couple to get the driving system. We're going to hit it with a 5-foot stroke in the first 20 feet, and then we can start easing that thing up. Helps you work out fuel settings and everything else as you're moving into the last production concrete piles. As I said, when we look at a pre-driving submittal, it's a best estimate. That's what we are doing. And as I told you before, our estimates are overestimates, and that's okay. But the PDA helps us to make that better. So you might, if we get into a situation where we try to drive a pile, we don't get bearing, we try redrive, we don't get bearing, we come back out and we run a PDA, you might find out that if we gave you a criteria of a 7-foot stroke and 48 blows per foot, you might find out when we run that PDA for that 7-foot stroke, it might be 35 blows per foot. Again, we overestimated previously. PDA helps us get it right the second time around. Okay. So here's your typical construction summary. For H piles, I think across the state, Chris's region included, the process is for an H pile, we're going to try to drive to get the resistance or get the bearing that we're looking for. If we don't get that bearing, then we're going to tell the contractor to stop. We're going to come back at least 24 hours later. We're into driving at 4 o'clock in the afternoon. We might come back at 10 in the next morning and hit them again. Okay? We're going to redrive them using those 2 blow sets. If we then by chance don't get the redrive bearing that we're looking for, then we're going to have to call the PDA out there because the PDA will let us analyze truly what the capacity of that pile, what the dynamic capacity of that pile is, okay? For pipe or concrete piles, typically, if there's a PDA in the contract, you'll get the memo and it says, the memo should say, the submitted hammer is suitable to begin dynamic pile testing, or PDA. So you'll move into the PDA phase. Again, we're always going to run PDAs for concrete. That's to make sure that our stresses, tension stresses are good. Maybe for pipes, again, checking our memo. If you get a memo that has a driving table on it, you're not running a PDA, you're driving those piles. Okay. Those two, pipes or concrete, may require redrives. Again, it's, if you're in a redrive condition with a concrete pile or a pipe pile, the two blow sets won't matter. Those piles won't take off like a H pile will. So we're into the 10 blow sets. Okay? Does anybody have any questions about pile driving? I'm going to try to do Chris's portion of this as best I can. Does anybody have questions about pile driving?
Can you touch on, you may have, I'm sorry, minimum tip? Could you touch on that a little bit?
Just briefly.
Briefly, yeah. Because these guys may not have as much. Lee's just telling me he didn't see that a lot in his plans, but we've got that more in our area. But I just want to make sure they understand that and look for it in their plans.
How many folks have ever had a pile bent, interior pile bent on a bridge? On those bridges, you know, there's always a note on plans that says not only drive the piles to a certain resistance or bearing, but also drive them to a minimum tip elevation, whatever. You know, I'll talk a little bit about it here. These are all Chris's pictures, mainly the eastern part of the state. I think he's got some Division 7 pictures in here. But where the minimum tip comes in has nothing to do with axial capacity, vertical capacity. It has to do with the fence post bending over condition. So part of the geotech analysis for a pile bend is how far that pile has to get in the ground before, you know, structural design provides us not only the vertical load but the horizontal load on that pile. So geotech looks at how far that pile has to be in the ground before it wants to bend over, just like a fence post. So that's where the minimum tip comes in. We've got to get that pile to that portion, to that elevation, in order to resist that load that we're looking for. Okay. So again, as the spec says, you drive the pile continuously until you get minimum tip if it's on the plans, if you get bearing or you get refusal. Okay. If by chance you get bearing before you get the minimum tip, we still drive, right? If by chance you get refusal before you get the minimum tip, we stop. We pick up the phone, we call, and we say, something's not right. We should not get refusal if everybody's done their job along the way. We should not get refusal before we get the minimum tip. Okay.
Now, don't confuse minimum tip with plan length pile.
Right.
Okay? Don't get that confused.
If you get the minimum tip, you get bearing, you can stop. I don't care what the contract says. You're supposed to have 80-foot long piles. Minimum tip, let's say, is 40 feet in the ground. You get to 41 feet, you got bearing. Pile's good. Okay. You don't have to drive it daily. Okay. It'd be a rare condition to not happen.
The reason I want to bring that up, I think on some occasions, some folks have been confused about scour, that scour critical elevation, and they thought that minimum tip was associated with that, but it's not. So that's just, we just want to make sure everybody knew that. That scour critical elevation is, from a design standpoint, it's as if the soil down to that level is not even there, right?
Yeah.
The piles are designed as though that material is not even there.
Yeah, the scour critical elevation is determined by geotech, and it is either the scour from the 500-year storm, or it's 2 to 3 feet below what geotech uses as the design scour. The design scour elevation is the 100-year storm, the scour that results from a 100-year storm. And what only, as the note on plan says, for scour critical elevation, its purpose is for bridge maintenance during their process of inspecting bridges, for them to you know, when they take measurements beside piles or beside drill piers or wherever, if they take an elevation shot and they see that that elevation is below the scour critical elevation, they are then prompted to take immediate action for that foundation. Okay, that's the purpose of that note. Okay. Okay, I'm going to try to do my best at Chris's portion. The top left-hand picture. This is double row battered piles. This is again down east, and the reason you've got a double row of battered piles here, these are big concrete, 20-inch concrete piles. The reason you've got a double row is a single row could not penetrate deep enough. They couldn't get to the minimum tip elevation in the design process, not in the construction process. But in the design process, because of a hard layer underneath, they couldn't get the big 20-inch concrete pile deep enough for one row to work. So they had to put essentially a frame in there, double row battered piles, to help with that pushover that bridge wants to put on those foundations. Lateral load on a bridge comes from two different directions. It comes from, you know, if you look at a bridge in elevation, the wind or water pushing against that bridge. That direction through the bridge tends not to be the bad direction. The bad direction tends to be along the bridge, and where that affects things are your bearings and beams sitting on those seats and getting those bearings in the wrong position, essentially. Those forces, and you might say, well, where does that force come from? That force comes from the tractor trailer rolling across that thing and locking up its brakes, trying to shove that bridge long place. So that direction from a structure standpoint, from a geotech standpoint, tends to be the direction that gets looked at the most. Through the bridge, you get that big frame. You've got that bent sitting there, and that big frame that helps minimize that kind of movement. Okay. You got 12-inch pipe piles at an end bend. How many folks have ever had a pipe piles at an end bend? That's a rare condition. Looks like they're getting ready to build a MSE wall out front because you can see all the piles sticking up. Another double row condition. This time it's H piles, battered. Again, limited penetration for that H pile, forcing them into a double row condition. Those piles are galvanized. Down in the bottom right, you've got footing on H piles, and it's really critical to make sure when you're driving those piles that you maintain good alignment. That means we need those leads to be checked for plumbness both directions. Because especially when you do a footing on piles in conditions like this, you don't want to get a pile out and not be able to get your platform footing form on top of that. So real important to make sure that the contractor's doing his job, making sure he's plumbing those leads in both directions.
Dean, that little slab on the bottom of those footings there is really not something that's in our plans. That was something the contractor proposed and got approval to do. And so it was a sacrificial slab they decided to use for their false work, or for the bottom of the footing. The water elevations fluctuate quite a bit, so if they had to use an extensive set of false work down there, it was going to be difficult if the water level came up to get that false work out. So they came up with a method to put that slab in and leave it in place. So it's got some reinforcing steel that actually ties up into the footing. We've used that in a few places in our area.
This is an example, top-down construction, big pipe piles. How many folks have ever been an inspector on a top-down construction job? It's real common where Kevin's from, where Chris covers. And the way it works is contractor drives his interior first bent piles, forms that cap, drives his end bent piles, gets that cap done. This is a cord slab bridge, and he sets his cord slabs across those two bends, right? He's got his end bent number 1, he drives his crane out onto the bridge at that point. He drives bent 2, he progresses across the bridge that way. The last bend he drives is the end bent 2. Okay? What that allows is, one, it's pretty fast. I mean, it's a good way to do it. It saves us money, saves contractor money. He doesn't have to build a work bridge, causeways, or anything like that. I think you may see a lot of this. I don't know if you guys have heard, but we've got sub-regional tier bridges now. If you've been on a bridge that we don't have the typical reinforced bridge approach field with all those different layers of fabric, we're putting a little wedge of stone underneath our approach slabs. Those are called sub-regional tiers. Those are low traffic volume, low risk bridges that we're trying to save a little bit of money on. A lot of divisions now that they're managing these a handful of bridges themselves each year, they're packaging these bridges together and sending them out as a package for design build type thing. And I think what you'll see, there'll be core slab bridges, short span, maybe 1-span, 2-span bridges, and I think you'll see a lot of this coming up. I think over the next 5 or 10 years, you'll see a bunch of top-down construction because of that sub-regional tier, low-impact bridge program. This is 2 pictures of bridge maintenance work, and bridge maintenance tends to do things a little bit differently. They don't have or really have the capabilities to go out and rent big diesel hammer, and a lot of bridge maintenance areas have drop hammers. We don't allow drop hammers on TIP jobs, but when bridge maintenance has a bridge that they need to shore up just a little bit at a bend, they'll bring out a drop hammer, and the way a drop hammer works is exactly the way it sounds. They lift up this big ramp and with the crane, and they cut loose the brake, and it falls and drives, in this case, an H-pile. And so they're building a crutch bent. They've got piles going bad, maybe timber piles that are rotting. So they go in there and drive piles either side and build a little crutch underneath that bent to try to get 20 more years out of this bridge. This is an example of how long piles tend to get down at the coast. Big 24-inch pipe piles. These are metallized piles. They way down east where you have to deal with saltwater, brackish conditions. Piles tend not to be galvanized. They tend to be metallized, which is a harder, better corrosion protection for piles. It provides, Randy, do you know how much longer metallization provides extra than galvanization?
I do not. I know it's quite a bit more expensive, but it is much more durable.
Yeah.
Very difficult to repair. There's not very many people who come in who can repair them.
Metallization is sprayed on, where galvanization is dipped. When the steel manufacturer provides the piles to the galvanization company, they've got long vats of zinc alloy, and they take that pile and they dip it in there, and that's what provides galvanization. But metallization it looks like textured sealing to me. I mean, it's sprayed on it. It kind of looks like that. But if you can imagine driving a pile through the ground, you need a coating that kind of resists all that abrasive action that's going on around that pile. Down east, again, you tend to get really long piles, and this is an example Chris has for installing piles initially with a vibratory hammer. Have you guys ever been involved with a contractor that wanted to install some with a vibratory hammer, at least to get them started? And we would allow that vibratory hammer to get those piles started, but only for about half the length of the pile. So if we're trying to install 60-foot long piles, we'd allow them to put a vibratory hammer on it until they got 30 feet to the ground. Then we're going jump on top of it. What a vibratory hammer does, if your ground is soft enough, with great depth, it allows him to set this template up, get that pile in the right location, and not be worried about getting out of location, trying to drive that in the ground. With really soft ground, any little movement, any out of plumbness with that hammer, he's started wrong, he's going to end up way wrong by the time he gets 60 feet of ground. Okay? These piles are galvanized only in the top portion, and if you get on a project with a pile bent, that's typically what you'll see these days. Let's say you had 20-foot long piles on a pile bent. The bottom 10-foot stick, and that's typically the way it would be. Contractor with 20-foot long piles would probably have 10-foot sticks of black steel and 10-foot sticks of galvanized. The contractor would take those two different piles, splice them together, and there should be a note on plans that requires the contractor to get the bottom of the galvanization to a certain elevation in the ground. Okay? And that elevation is deep enough in the ground that the black steel won't corrode, and we still have protection for what's exposed. Typically, when we get a project like that, we're not, let's say the 20 foot's a bad example. Let's say we're thinking we've got 60-foot long piles. That galvanization elevation that we need to get to may not be well known before we start driving the pile. And so we may recommend to the contractor, we can't make him do it, but we may recommend to the contractor that the first pile we drive, let's say we drive the middle pile in a bend, we may ask him to, or we may recommend to him that he drive the first pile he drives be fully galvanized so that we can figure out exactly where we're going to end up. That way we don't screw up the first one. If we drive that first pile and he's got in his mind that he knows exactly where everything's going to end up. We drive that pile in the galvanization, we got black steel, 5 feet above where it's supposed to be. We've got to then extract that pile and then go at it again. Okay. You want to talk about pay items for that?
I think with this, as I understood it, this pay item used to be is two separate pay items. For the same pile, if you have, like he was just talking about, I'm sorry for stepping out, but the bottom part being black steel, the top being galvanized, we used to pay for that as whatever they drove for black was paid as that, and the galvanized portion was paid as galvanized. Well, I guess there were some issues with that, trying to get elevations figured out and everything else. And we now, I believe, have one single pay item for this, and it is galvanized steel piles. So don't be confused by your pay items. Look to make sure that that's the way it's listed, and it should be shown that way to bill of materials, I'm thinking, but it should just be the one pay item. So even though you're driving some black steel for these piles, it's going to be galvanized. That's the pay item, just to simplify life, and you got one pay item for one pile.
I think the confusion, there'll still be two pay items in the contract. One for
yes.
One for H piles and one for galvanized H piles, or however it's called out. Just don't get confused. Again, like Kevin said, look on your bill of material and see how it's spelled out in there. But to make everything clear these days, if you drive a pile that's galvanized, whether it's got a portion of black steel on it or not, the thinking is that it's going to be paid as a galvanized pile. But again, check the bill of materials.
The reason that you still may have the typical H-pile item, not the non-galvanized version, is we're still driving black steel for our indents. Bridge maintenance jobs, they actually, for the contracts that they let, are typically calling for galvanized piles for all bends. The problem that they're seeing on indents is over time, some of that embankment actually begins to settle, or either there's scour up underneath the cap, depending on the elevation of the cap and the elevation of the creek or stream or whatever they're crossing. That separation underneath the cap has caused some issues with corrosion of those piles. So they have always called for galvanized piles. Now what you're gonna see, how many of you seen the new detail with the concrete collar around the upper portion of indent piles? Got a couple folks, so anybody else seen that? If you have not seen that, you should be looking for any plans coming out now for indents. You're gonna see a collar that's shown around the upper 18 inches of the piles for the very reason I just described. Our folks are structure design, construction units, and all, we're not quite ready to commit to going all galvanized piles because of the expense. So we tried to compromise with bridge maintenance, and this is what we came up with, was putting the collar around that upper 18 inches in case the embankment settles, in case there's scour underneath the cap, and that protects that upper portion of the pile from corrosion. The way you go about that is you can either use a sonotube for the form. You can, if your soil is stiff enough, you can excavate it out, just leave it like that. That collar is poured with the cap. So you guys need to be watching when they're making that pour, make sure the concrete is getting down in that hole good, that they're vibrating that concrete into place. They can form it up square if they want to. We don't really care as long as you've got that minimum amount of concrete around the perimeter of the pile on all sides. So whatever your contractor wants to do there, we've got a lot of flexibility with how we go about putting that in.
Will that be in all areas of the state?
I believe so. I've not been, no one said anything about that being for specific areas. As far as I know, these guys are having, we are too in the east, so it's, and I think that's out now on all planes. At least all Raleigh-led TIP type planes. So bridge maintenance job, like I said, you'll still probably see the galvanized piles instead of that.
This is a picture of a steel pile point, and it is not galvanized because it's sacrificial in the driving process. So even if you've got galvanized piles on a project, steel pile points will tend to come out just black steel.
Contractor allowed to make their own pile points?
No, there's an approved list of pile points that he would choose from. They're fairly expensive, but they're really important. You know, in my part of the state, especially if you're driving to rock or driving to a high tonnage, pile points are real important, because if not, you know, if you've got a 250 ton 14 by 73 pile going in the ground, maybe 300 ton 14 by 73, it takes a lot of penetration in the weathered rock to get that kind of tonnage, and it's pretty likely that during that penetration in the weathered rock, those flanges are going to start to bend. And so that pile point helps the penetration, plus it stiffens up all those flanges.
When it first come out, they probably beat it up and build their own.
But it really helps. It also helps with power.
Yeah. In a hard rock condition, they're real important, especially if you've got a sloping rock, to keep that pile from wanting to walk that rock. This is an example of, I'm not going to talk about the holes, I'm going to leave the holes for Colin. Yeah. This is an example of galvanized pipe piles, and the one thing that I'll talk about, and I'll leave the VCEs to wade into the manure of torch cutting holes. If you're working with coated piles, whether that be metallized or galvanized, it's important that when the contractor set up his template, that we provide some cushion for those piles through that template. And the best way to do it is with wooden blocks along that template. He may still have steel angles, you know, providing alignment for those piles, but we want wood blocks sitting inside those steel angles on his template, so that as that pile squeals its way into the ground through that template, we're not rubbing off the metallization or galvanization. So keep that in the back of your mind. Make the contractor go the extra mile. We're paying for that galvanization. The last thing we want to do is wear it off before we put it in the ground. Now the BCEs are going to talk about the torch cut holes at the top.
How many of you have seen that? Piles come out, torch cut holes, or well, they don't come out with torch cut holes. The contractor torch cuts a hole in the pile so he can lift it. We're still okay with that, but if they torch cut a hole in the pile, we want to cut that off. Period.
And Maxine contract
Yeah, the logic in the past has always been, if it's gonna end up in the cap, it's nothing to worry, you know, no big deal. What we really wanna do is get to the point where we're discouraging contractors from doing it all together. They gotta go to the effort to cut off, a torch cut hole, then they may start not doing that. What we really wanna kinda get them to do is start punching these holes at the fabricator, and then when they galvanize the pile or metalize it, then they're treating that hole at the time, you know, the hole's already there, they're galvanizing and taking care of it at that point. And if that's the case, if it comes out that way, either with a drilled hole or a punched hole, it's been galvanized, we don't have a problem leaving that in place. The other thing we don't want to do is to weld a steel plate of some sort over the hole. And that creates some other issues in itself. It creates a hard spot in the steel, and you know, that little weld, the cracks can begin to propagate from that welded steel plate, depending on the movement of the pile. And granted, you're not going to have a whole lot of movement there, but there are obviously subtle movements in these piles, and we don't want those stresses to cause cracks. The big question we always get, well, gosh, if you can't weld a steel plate on there, you're welding two sticks of pile together. You know that you got a big gigantic weld that goes all the way around. What's that doing to it? Well, that's something that's been looked at, evaluated, and is an approved weld, and that's something that we're not concerned with. The pile still reacts and functions as it should with that weld, but the welded on steel plate over a hole can cause some issues. So, is that clear as mud? Everybody got that? So just really the main point I want to drive home here, if you torch cut a hole, cut it off. Get them to cut it off.
How far down would you cut it off?
2 or 3 inches below the hole.
Yeah.
The other thing is,
Yeah.
especially for pipe piles, is some contractors have asked, can we burn holes in them to hold false work for the cap?
That's really what, Darren, I'm glad you mentioned that. Eddie was just reminding me that I had a bridge here recently where we had 2 contractors working on the same bridge. They were working from both indents towards, they were going to meet in the middle. And one was using hanger system from the top of their piles for their cap, false work. The other was torch cutting holes through the pile to hang just like you would the holes in a concrete column. Run that big bolt through there and do it that way. They were doing the same thing with a pipe pile. And we kind of called it after the fact, but we really put a stop to that. We don't want to allow that anymore.
Now, Dean touched on issues about preventing damage. You can see the damage right here to these galvanized piles. Well, sometimes it's going to happen. Well, from what these guys have been telling me after they do a 12-month review, what they're seeing is these areas that have been touched up are having to be repaired after that 12-month review, because they've got rust bleeding through. So if you do have to touch up, one thing, make sure that the material that they're using, the paint that they're using, meets our specifications. And in addition to that, when they bring that material out, it should be a 2-part epoxy zinc-rich primer. They should have an application data sheet. This application data sheet will tell you what kind of metal preparation is required, what kind of ambient conditions are required. Okay, so if the humidity's too high, they're not supposed to use it. And also, they're supposed to put 2 coats. This application data sheet will tell you what kind of curing time is required between coats.
The coatings on these piles are expensive. We want them on there for a reason. You know, Dean hit on the wood blocking to protect them, but also storage on the job. You know, contractors go out there and start stacking them up, don't do a good job of blocking them. You can damage piles that way, just improper handling, so that's something we want to keep on top of. We're paying a lot of money for that coating, and that any kind of touch-up paint that we do is never going to be equivalent to what the original coating was.
It's a fraction of the effectiveness.
That's right.
Yep. I mean, keep an eye on the piles, not only, you know, as we're driving them, but, you know, inspect what's laying out in storage. Make sure that if you see anything with some damage to the coating, make sure the contractor go ahead and repairs that. Because, you know, once pile driving starts, the last thing on your mind is that galvanization. So, you can see the painted areas here, splices, nicks, everything contractor painted. Again, what Randy said, make sure that they're doing it right. Is there an approved list of paint or is it's just, it has to be within spec?
Our specification has guidelines for the properties that this paint needs to be in. And so we do, when it comes to repair paint, we do not have that on an approved list.
I think the key thing also is keeping it agitated, Randy.
It is, but that primarily is talking about the paint that they use in a shop environment. The application data sheet on this two-part epoxy will tell you the kind of mixing requirements and so forth also. Continual agitation is usually what they use on an inorganic zinc-rich primer.
So a few pictures of PDA testing. For those of you that've seen it before, you can see the gauges here mounted. Those are the accelerometers, and there'll be one on this side. On a square pile, you have to do both sides. On a H pile, they tend to hang them from the web, and it's just one. There's the computer equipment, and as a PDA is going on, you can actually see all the data, what the stresses are, what the capacity is, all of that. And at the end of a PDA, you tend to have a decent idea of whether you've got the capacity that you're looking for. Composite piles. I started late. It's Kevin's fault. Composite piles, this is something down east, you'll probably never see anything like that here. Concrete piles, again, it's easy to damage concrete piles. If you ever drive concrete piles and you get some cracking, get some damage, typically what we'll do is cut it off below the damage, and then there's a build-up detail in the structure plans that will allow the contractor to chip that down and build a new concrete section up. But as we learned in Division 8, if you're driving a pile, these are all pre-stressed concrete piles. They have steel tendons in them, kind of like a cord slab bridge. If you're driving a pile and you run out of pile, there's no way to make that right. You can't build it up and re-drive it again. So it's real important for the contractor to get right concrete pile lengths out on this project. Chris got a picture of debris loading over there on the left. You can see all the pile of timber loaded up there. If you're out on a project, keep an eye on stuff like that. Temporary work bridges, temporary detour bridges. I won't get into the discussion of who's responsible for that. These, we talked about driving piles. These are H piles. H piles that were driven through boulders. Looks like sheet piles at this point. So, again, check your borings. Sometimes Geotech doesn't get the borings right. Every once in a while we'll get them. But if we're expecting, and you know, it's not only if you look at building materials and you take the average pile length, don't just go by that average pile length. Look at those two end-bit borings. You know, you might have an average pile length of 30, but you might have, 25s on one side and 35s on the other. Still an average of 30. But look at that. Know where a pile's supposed to take up, and if one by chance takes up 10 feet short, don't sit there and keep beating it, trying to get that extra length out of it, because this is what you'll end up with. Something else is going on in the ground, and we got to figure out what it is.
Dean, real quick on that debris loading, it may not seem like a big deal, but it is. We had a pile similar to that on a work bridge. Now, granted, we didn't have traffic on this. This is just the contractor's work bridge, but it was starting to concern us, and we told the contractor, look, you need to go back to your designer and get their input on this, because we kept telling them they need to get it up, and they didn't want to mess with it. The minute they talked to their designer about it, the designer said, you need to get the crane off of that bridge till you get that, or you need to reach out from away from there and pick that stuff up and get it out of there now. Because they didn't factor in all that lateral loading on the structure. So that's something we certainly need to keep an eye on, particularly on a detour structure when we've got traffic on it. It may not be designed for all that additional loading on it from the side. So just something to keep in mind.
Drilled in piles, won't spend a whole lot of time on that. I would assume maybe some of you have seen pile excavation on the project. We'll drill down into weathered rock or hard rock, stand the pile up inside of it. Typically, when we write a memo out of my office, if we've got pile excavation, basically my instructions are, if you drill that hole, if the hole's clean, if you're in rock, you can stand the pile up inside of it and fill it up with whatever the contract tells you to fill it up with concrete. If by chance you get down to the bottom and you can't tell whether the hole's clean or not, you're not sure you're in rock, then we're going to stand that pile up and we're going to put the hammer on top of it. We're going to barely fire that hammer and we're going to hit it until it stops. Once it stops, we're done. We're down to where we're supposed to be. We're going to fill it up full of concrete. Okay? Piles behind a MSE wall. Thing to keep in mind here is help the contractor think. They won't always listen, but help the contractor think of, if you've got an MSE wall that's 25 or 30 feet tall and an end bend, they're putting those piles in before they ever start building this wall. As you're compacting all this stone around all those piles, you have a tendency to be able to shove those piles around, okay, move them. So the last thing you want to have happen is you top out that MSE wall 25 feet tall, realize that all your piles are shoved around. So help the contractor think through those things and make sure that, he takes the actions necessary to make sure those piles are in the right spot, okay? Sometimes they won't listen. Any questions? Okay, we're going to take a break.